So welcome to another chemistry revision video. In this video we're going to cover chemical changes, reactions, how chemicals react, and metals and acids, and electrolysis and reduction and oxidation, and all of that good stuff, as well as half equations and ionic equations if you're doing higher tier. It's kind of the pinnacle of chemistry, if you like, or chemistry paper 1 should I say, where we put together all the stuff that we've covered so far in the previous three videos, which you really should go and watch if you're not entirely happy with bonding and concentration calculations and how elements react and the groups of the periodic table. Those are all really important to understanding a lot of the concepts in this video, because I will mention like all the concepts, how ionic compounds fit together and bond together with the different amount of electrons and everything. So we're going to get into it, have a look at the advanced info first. So nothing has been taken out for anyone from this topic, because barely anything has been taken out from chemistry. So if you're Combined Science Foundation, your major focus is all three topics, but obviously none of the higher bits, and your required practicals are the soluble salts one and the electrolysis one as well. Combined Science Higher, again, your revision focus is all three topics that we cover in this video, again, as well as the soluble salts practical and the electrolysis practical. If you're taking chemistry as a separate science, or triple science as I refer to it, and you're on the foundation tier, then your major focus is the reactions of acids bit, minus of course the strong and weak acids because they're higher tier only. If you're doing foundation tier, you won't need to worry about them, so there's actually not too much to focus your revision on, but everything else might be tested a bit as well. In fact, it will be tested a tiny bit. And your two required practicals are the soluble salts practical and the titrations practical. And finally, for your triple science higher, your revision focus is all three topics, and your practicals, again, that we see the soluble salts practical, that's coming up for everyone, and then your other required practical is titrations. So we're going to begin our journey through chemical changes and all kinds of reactions through a look at reactivity in metals. So if you want to pause the video and have a go at these 21 questions, the bold is higher tier only. So, the reactivity of metals depends on how easily they can lose the electrons on their outer shell and form positive ions. So this is drawing on things we've discussed in the previous videos, because all elements react to get a full outer shell. Metals, by definition, react to form positive ions, which means that they lose electrons. And because of this loss of negatively charged particles, the positively charged protons outweigh the negative charge of the electrons, and therefore they're positive ions. So now we're going to have a look at the reactivity series, which kind of underpins this whole topic of reactions with metals, because it shows how well different metals react. It kind of shows the order, because at the top we have the most reactive metals, and at the bottom we have the least reactive. It's the order of reactivity, essentially. So you have to remember this. You just do, so that you can answer questions about, again, compounds you've never heard of. But before I start going through it, carbon and hydrogen are often added in, even though they're non-metals, just because a lot of reactions feature them. So we start with potassium, sodium and lithium. What do you notice about all of them? Well, you should have noticed they're all group 1 elements, so alkali metals. These are the most reactive because they only have to lose 1 electron, and we talked about why going down the group it gets more reactive in video 1, if you want to go check that out. And then calcium and magnesium, these are both group 2. Calcium is lower down in group 2 than magnesium is. So these first 5 are quite easy to remember on the basis of the stuff that we covered about group 1 in the first video on the atoms and the periodic table and everything, on how they lose electrons, because these have more electrons to lose. Potassium, due to electron shielding, can lose its electron more easily. Then we get carbon, and then after that we begin to get on to the transition metals. Again, properties of transition metals, a triple science only topic. They are less reactive than the alkali metals and the alkali earth metals. So zinc and iron, the order of those is probably trickiest to remember. Zinc is more reactive than iron. Then we have hydrogen here, and then below hydrogen we have copper, which is fairly unreactive, and then below we sometimes write silver, gold, then platinum. So displacement reactions are quite interesting. If we look down to 4, basically what happens in a displacement reaction is one metal, it's more reactive, and more reactive metal kicks out another metal from its compound. So ionic compounds we see here, copper sulfate plus magnesium. The reaction happens here because magnesium is more reactive than copper. This is why you need to remember your reactivity series. So magnesium displaces the copper, and our products are magnesium sulfate, so MgSO4, and copper on its own. So that's basically what displacement reaction is. If we had magnesium sulfate and we added copper, there would be no reaction because the copper is less reactive than the magnesium. Displacement reactions, it's generally easy to get your head around. So a higher tier only equation that you could be asked about in chemistry are ionic equations, and they basically just show how ions change in chemical reactions. So for example, the most basic, the bonding of sodium and chloride here. We have sodium and chlorine atoms. You know there's no symbol of charge, but when they react and bond, obviously the sodium gives up one electron to the chlorine, and that forms sodium chloride. So we symbolize the sodium has formed a positive ion, so we put plus. If it was magnesium, we would put 2 plus, because that's like how many electrons it's lost, so that's its relative charge essentially. And chlorine is minus or 1 minus, but you don't generally put the 1. It's like in maths, when you have coefficients. When 1's the coefficient, you don't write it. But anyway, so here a generic ionic equation again, this time shown with the displacement reaction that we just had, where magnesium displaces copper from copper sulfate to form magnesium sulfate and copper. This is the normal chemical reaction. But here we have the ionic equation. So here we have the Mg, because it's an atom, we have just Mg atoms. And then copper sulfate is bonded. You're not expected to know the charge of transition metals off by heart, but you would be able to figure out that because magnesium is in group 2, it's going to form a 2 plus ion because it loses 2 electrons, but you don't need to know that for transition metals. So for this one, we have the copper has given 2 electrons to the sulfate, but then when it's displaced, the copper takes back its 2 electrons and is booted out and is produced as a copper atom, whereas magnesium ends up in the compound as a sulfate, and it gives its 2 electrons on its outer shell to the sulfate, and it forms a 2 plus ion. So that is how we write ionic equations. We only write out the bits that change in charge. The SO4, the sulfate ion, would be called a spectator ion, because obviously this would be 2 minus, because it has 2 gaps for electrons in the whole sulfate. You don't need to know how like sulfates are bonded, but that's the ion. It'd be a 2 minus. And we call it a spectator ion because nothing happens to it, it's just there, and elements are fighting over it. So then, what happens when metals and acids react? So metal plus acid always gives you salt plus hydrogen, and we're going to look more at salts and how they're made and how you figure out what the name of the salt is from the reaction between the metal and acid just in a bit. But metal plus acid equals salt plus hydrogen. So the salt in magnesium plus hydrochloric acid would be magnesium chloride, and then we get hydrogen given off as bubbles. So in answer to question 7, how do they react with dilute acid? What would we observe in this reaction at room temperature? Well, the more reactive ones, these 5 up here, the non-transition metals are more reactive. We're going to see them react vigorously. Lots of bubbles of hydrogen. The amount of bubbles with hydrogen indicate how fast the rate of reaction is. So we're going to have a vigorous reaction with lots of bubbles. Maybe like zinc and iron, we're not going to have as many bubbles. It's going to be pretty slow. And copper is going to be slow, not at all. As we get into silver, gold, it's kind of not at all. Again, they react more as you heat them up, but the specification is specific. It says that you only need to know their reactions with acid and water at room temperature. So how do metals plus waters react? Metal plus water gives you a metal hydroxide plus hydrogen. So it's a similar thing, but instead of the acid hydrochloric acid, we have water, H2O, so we get the metal hydroxide instead of the salt, and again, still the hydrogen given off. So how do these guys react with water? So we have our cold room temperature water, our 5 most reactive ones from groups 1 and 2. They're going to react. Potassium, obviously we cover the reactions of group 1 and water in the first video, didn't we? We described how potassium would burn with a lilac flame. There's vigorous reactions, getting less vigorous. Maybe zinc might react a tiny bit, but it's likely that zinc, iron and copper with cold water or water at room temperature, they're not going to react at all. So here's some examples to test your understanding of the metals plus acids, metals plus waters. Again, you could be asked about any of them. Hydrochloric acid and sulfuric acid are likely to be the two that you're going to be asked about. Maybe nitric acid as well. We'll cover that when we look more in detail at acids in a bit. But for now, remember that hydrochloric acid is HCl and sulfuric acid is H2SO4. So here is the symbol equation for the reaction between potassium and hydrochloric acid. I know it may look like another language, but 2K, 2 moles of potassium plus HCl gives you potassium chloride as the salt. And again, we can, this simple ionic compound, we can figure out if we needed two potassium. Well, we've got group 1 and 7, so 1 electron fits perfectly to add 1 to make 8. So we don't need 2 potassiums. If it was magnesium, we would need 2 magnesiums. And H2, because hydrogen is diatomic, we cover that in the first video, we need to balance it out, so all the others have to have 2s. So zinc plus sulfuric acid, H2SO4, gives us zinc sulfate, again plus hydrogen, 1 to 1 to 1 to 1 mole ratio, because everything's perfect, which is quite useful. Oh, and it's worth noting state symbols. You might be asked to put state symbols on any one of these reactions. So the metals, they're going to be solids, aren't we? We discussed how metals, because they're metallically bonded, they're going to have a high melting and boiling point. We went through this in the second video. Hydrogen, H2, it's going to be a gas because it's a simple covalent molecule. Again, go through the second video. You can kind of see how each topic builds upon the next to give you these layers of understanding in chemistry paper 1, and which is so important for you to be able to complete the paper. And both acids and salts, which we have here, are both aqueous, and that's something you should probably just remember, that salts, generally ionic compounds, are usually aqueous, dissolved in water, and acids, as we come on to later, they've dissociated, but yeah, we come on to that later. That's higher tier only as well, I think. And finally, our metal plus water reaction, magnesium reacts with water, and this is magnesium hydroxide here. If you remember, metal plus water equals metal hydroxide plus hydrogen. This is how we write it. It kind of shows that we've got these OH ions with the negative ions with the magnesium positive ions in our ionic metal hydroxide compound. We put them in brackets with a 2 to show we've got 2 of both. And state symbols, once again, solid, liquid, aqueous, gas. So a bit of everything, really. Before we get started on the extracting metals questions, because we've got some spread out kind of higher tier bits, the higher tier bits of half equations, anything ionic or half equations, explaining oxidation and reduction in terms of gains and loss of electrons is higher tier, but in terms of oxygen it is not higher tier, and redox reactions are higher tier as well. So we find metals naturally as metal oxides simply because they've reacted with the oxygen in the air. When they've been in the air, they may have gotten buried underground, but apart from most unreactive metals, you'll find most metals as metal compounds, usually metal oxides again, because they have reacted with that oxygen in the air. So there's a separating technique that we use to get the pure metal, which is called reduction, and it's simply reacting our metal oxide with carbon, and what happens is the carbon becomes oxidized, which means it gains oxygen, and the metal becomes reduced, which means it loses the oxygen, so you get the pure metal on its own, and often, yeah, carbon dioxide, because the carbon's been oxidized. Which metals cannot be reduced is question 7. That's interesting. Any metals more reactive than carbon cannot be reduced because it's kind of like, or cannot be extracted by reduction, I should say. They can still be reduced in some ways. This is because they're more reactive than carbon, so no displacement can take place. Because if you think about it, it's kind of a displacement reaction in a way, because the carbon is displacing the metal from the oxygen and kind of taking the oxygen. You know, there's multiple ways of looking at these chemical reactions. So the higher tier bit describe oxidation in terms of electrons as well. So we generally say that oxidation, you'll gain the element that's being oxidized, or the compound that's being oxidized, is gaining oxygen, and reduction, it's losing oxygen. But sometimes we can have oxidation and reduction where there's no oxygen involved, and this is simply because oxidation is a loss of electrons to form a positive ion. Think about that. When your metal is reacting with oxygen to form an ionic compound, the metal loses electrons because it gives it to the oxygen. So oxidation of a metal is loss of oxygens, and reduction, therefore, is gain of electrons. So there's a nice acronym, yeah. Oil rig. Oxidation is loss, reduction is gain. That's how you remember. You say oil rig, oxidation is loss, reduction is gain of electrons. Or you think about the ionic compound and the metal. If it's being oxidized, it's giving its electrons away and therefore losing electrons. Or if it's being reduced and it's like kind of coming away because it's been displaced from an ionic compound, it's taking those electrons back and gaining electrons. So reduction is gain, oxidation is loss. Oil rig. I thought this one would be quite interesting to balance. So this is the reduction of iron oxide. So we have iron oxide here, Fe2O3. We're adding carbon, so we're reducing it to extract iron on its own. Note that carbon is from group 4, so it's not diatomic, and the carbon is being oxidized to get CO2, carbon dioxide. So how are we going to go about balancing it? Well, we need to make both sides the same, don't we? So we have 2 ions on this side, 1 ion on this side. So we can add 2 to here to get 2 ions. So ions are balanced. And now here's quite an interesting one, because we have 3 oxygens on this side, but 2 oxygens on this side. Now we need to make them equal, but we can't have like times 1.5 moles. No, mole ratios have to be whole numbers, just like ratios in maths. So we got times this one by 2 and times this one by 3. So what we're going to have to do is we're going to have to put a 2 in front of the one where oxygen is free to make 6 oxygens. And we also have to take into account how this changes the iron. So now instead of 2 on this side, we have 4 iron, but this is necessary to get our oxygens balanced, because we add 3 onto here to make 6 oxygens on this side. So 6. But always remember, when you're adding 3 onto compounds, it affects every single atom in the compound. So 3 carbons now as well. So now we've got to look at how we can balance our oxygens again. No, sorry, not our oxygens, our ions again, because we have 4 on this side and 2 on this side. Again, we've got to times this one by 2, which means putting a 4 there instead, so that we have 4 on both sides. So our ions and oxygens are balanced on 4 and 6. Our carbons are not. We've got 3 on this side, 1 on this side. 1 times 3 is 3. So what we're going to have to do is add 3 to this one to make it 3. And now we have the same number of atoms on both sides. We have our mole to mole ratio, and therefore our balance symbol equation for the reduction of iron oxide to get iron as a pure metal. So that just about answers questions 1 to 7. Question 8, why would we not reduce gold? Well, I discussed this at the very, very beginning. Gold is very, very low down on the reactivity series. Gold is very, very, very unreactive. barely reacts with anything at all. So gold does not react with the oxygen in the air, so we find gold in the Earth as a pure metal. So a higher tier topic, redox reactions. Reduction oxidation is where one term is reduced, well, I say one term, one of the reactants is reduced, one of the reactants is oxidized, or one of the, so something in a chemical reaction is reduced, something in a chemical reaction is oxidized, something in a chemical reaction loses electrons, something in a chemical reaction gains electrons, which is quite usual of chemical reactions, to be honest, because it's all about the exchange of electrons to get that full outer shell. So you'll be surprised at the amount of reactions come under this term redox reaction. And in fact, our reduction of iron oxide, this comes under a redox. This is a redox reaction because while our iron is being reduced, our oxygen is in fact, our carbon is in fact being oxidized as it gains oxygen, and the iron loses oxygen. But remember, this is higher tier now, so we don't look at it as oxygen, we look at it in terms of electrons. So what's happening with the iron is it's kind of being separated from its ionic compound, it's a bit or displaced, we might say. So this is gaining electrons as it's being reduced. Reduction is gain. Rig, part of the oil rig acronym. Carbon is over here. We have our carbon being oxidized because it is losing electrons while it shares with its electrons with the two oxygen molecules. So, higher tier, I've already introduced you to ionic equations. Now I'm going to introduce you to half equations. Half equations simply show the loss and gain of electrons really by writing them out. So we can show how iron is being reduced here. So iron oxide here, well, you don't have to know the exact amount of electrons iron has on its outer shell because it can vary, as we learn with transition metals, but we can actually work it out with the compound that we've been given, because oxygen, if we need 3 oxygens for the empirical formula, then that's 6 gaps for electrons, isn't it? And how can 2 iron atoms, electrons, fill 6 gaps? 6 electron gaps? Well, with 3 electrons in each gap, because 3 times 2 is 6. So from this we know that we're dealing with iron-free oxide. So we write this as Fe3+ up here to represent that this is a positive ion at the moment because it's given away 3 of its electrons to the oxygen molecules. So how we represent this is we show that the electrons separate, and as the iron is reduced, it's kind of getting its electrons back, isn't it? Because reduction is gain. So we are adding on the electrons because each electron is a charge of -1. And after reduction, we are left with the atom. It has no charge because it's an atom, not an ion. We need to balance half equations, which is it's very, very similar to balancing chemical equations. You just have to look at the charge, and then you need the amount of electrons that this ion is missing. So it's given away its 3 electrons. So 3 electrons are going to come back, aren't they, if we're going to make an iron atom with an equal number of electrons and protons. So we have to have 3 electron minuses. Electrons never have a little number down here because electrons don't bond. So now, how would we write a half equation for the oxidation of carbon? I'll leave you to pause and have a go, see if you can figure it out. So we're going to start this time with our carbon atom, just normal, it's over here, and how is this going to be oxidized? Well, it's going to gain oxygen, isn't it? So it's being oxidized, and what's that? A loss of electrons. It's basically reduction backwards. So what we're going to get is we're going to get C4+, because in our covalent bond you can draw out a dot and cross diagram for it if you want. You might need to for your exam. If the carbon atom is sharing 2 electrons with each oxygen, so it hasn't got a charge. The carbon doesn't react and gain charge in a covalent bond, but for like water, for example, let's take water. Later we're going to look how water can dissociate in an aqueous solution, in electrolysis, and turn into H plus ions and OH minus ions. This is quite a complicated area of chemistry, but I hope that you can see how we've got our 4 plus carbon with 4 charge, because it's sharing 2 electrons with each. So if we hid the oxygen for a second, we'd find C4 plus, but that's obviously ignoring the fact that the oxygen is also sharing a couple of electrons to give the carbon a full outer shell. So how are we going to finish it? Well, we're going to have E minus. How many E minuses are we going to have? We're going to have 4. However, we are not, these aren't balanced. One of the key things to do is you've got to look at the reaction that your stuff is coming from. So if we were writing half equations specifically for this reaction, we need to take into account the mole ratio. So we finish up with 4 Fe, so this has to be 4 Fe. So we need to start with 4 Fe to get 4 Fe out, 4 iron out, and therefore what does this have to be? Well, if we have 4 times 3 plus ions, which means that there's there's 12 electrons to gain in total, so this has to become 12 here, and this is our finished half equation, particularly for this reaction. Again, the end result looks quite complicated, and I bet 5 minutes ago if I showed you this you would have no idea what I'm on about, but I hope now you can see what the steps that we've gone through to get here, from getting the charge of the ion from the equation to getting the electrons and using the mole ratio to figuring out how much of each we have, and ultimately how many electrons. So let's do the same thing with the carbon. We are starting with 3 carbons, so we're going to end up with 3 carbon 4 pluses, and this means that once again we need 12 electrons. So you can kind of see that, like the oxygens, they had their 12 electrons taken away from them when we took away the iron, but then when the carbon kind of displaced the iron, it gave those 12 electrons back from its own 12, if that makes any sense. But yeah, this is how you do half equations. I hope you can see. We're going to go through another example. So what reaction happens between zinc and calcium sulfate? As we've covered the 9 questions, we're on to question 10 now. No reaction, actually, because you can see that zinc is less reactive than calcium if you go back to the reactivity series, and therefore zinc will not displace calcium. However, the reaction between calcium and zinc sulfate, there is a reaction because calcium is more reactive, so it's going to displace zinc sulfate. So let's have a go at the balance symbol equation and see if you can write half equations to show how this is a redox reaction, and have a go at an ionic equation as well. See if you can get all the different kinds of chemical equations in there. So here's the balance symbol equation. You should be able to then work out the ionic equation because obviously zinc has given 2 of its electrons to the sulfate, and then as it gets kicked out, it gets reduced because it gains electrons and becomes a zinc atom, whereas carbon gets oxidized and becomes a 2 plus carbon, did I say carbon? Calcium, a 2 plus calcium ion. And finally, here are the half equations. As you can see, calcium is being oxidized because oxidation is loss, reduction is gain. Oil rig, remember that acronym. So it's lost 2 electrons as it's given them to the sulfate ion, while zinc has been reduced because it's been kicked out in the displacement reaction. So again, it's gained 2 electrons. And what this means is displacement reactions are redox reactions because we have both reduction and oxidation going on. But again, this is higher tier. The ionic equations, the half equations, the idea of a redox reaction is all higher tier. The actual displacement reactions aren't, but the rest of it is. So now we're going to move on to reactivity in acids. So there's 28 questions here, but a lot of them are higher tier only, like all the half equations and redox reaction stuff. This first bit is kind of a bit of what we've just done. And this blue bit, titrations, is triple science only, not for combined science. And this bold bit, strong and weak acids, this is also higher tier only because it gets kind of complicated with dissociation of ion. Yeah, we'll get onto it. So pause and have a go. So, metal plus acid, I believe we did actually cover this in the last bit, so it's a good refresher because this is really, really important. Again, this is one of the backbones of this. Metal plus acid gives you a salt plus hydrogen. They could give you a random metal and a random acid, and you need to identify the products salt and hydrogen. You need to figure out what kind of salt. Don't just put salt, because there's loads and loads of different kinds of salts. This is a redox reaction. You need to know that for higher tier, because reduction and oxidation happens because there's gains and losses of electrons. So, for example, our metal plus acid here, our hydrogen gains an electron and is reduced, whereas our magnesium gives its electron to the chlorine ions and therefore is oxidized, loses an electron. Remember, oil rig, oxidation is loss, reduction is gain. So magnesium plus hydrochloric acid here, you will need to know how to complete it and balance it. So it's all stuff you can do though, because we know that metal here plus acid here gives you salt plus hydrogen. So what's the salt going to be? Well, salts, as we covered in video 2, salts are ionic compounds pretty much. That's that's pretty much what you need to know for GCSE level. And we get hydrogen, so we can pretty much figure out that when the hydrogen gets taken away, we're going to be left with magnesium chloride, because if you remember ionic compounds again from the second video, go and watch it if you haven't. It's really essential to understand this topic, because ionic bonding is not metal plus non-metal. We need to figure out the composition of the ionic compound, don't we? So chlorine has 1 electron gap to fill because it's in group 7. Magnesium has 2 electrons in its outer shell, so we're going to need 2 chlorines. Yeah, go and watch the second video if you don't understand how that works, because that's really important in understanding ionic compounds. And then we get H here. What's wrong with this? What's wrong? What am I missing? I'm missing a little 2 because hydrogen is diatomic again. That we covered that in the first video, and I think the second video as well a bit as well. That's important to know. Now balancing, we have 1 magnesium on both, but we need 2 of these on both, so we can just add a 2 here. Didn't bother writing out numbers underneath because was a very simple one to balance. Right, I want to see if you are able to write half equations for our magnesium and our hydrogen. So try and have a go at that. Remember, we're not doing one for chlorine because these are our spectator ions. Nothing really happens with them. They kind of just change partners, if you like. So is this reduction or oxidation? Remember, so we can see here we're losing electrons going from an atom to a positive ion, so we're losing electrons, so it's oxidation. Very good. So what you can see here, because magnesium is in group 2, it's got 2 electrons in its outer shell, so it's going to react to lose those 2 as we discussed here, so it's going to form a +2 positive ion, because it will then have 2 more protons than it does electrons, giving it positive charge. And this is how we write 2 electrons. Remember, we never put 2 minus up here. So for a challenge in the reduction of hydrogen, how many electrons is it going to gain? 1, because hydrogen it only ever has 1 electron. So is zinc oxidized or reduced when it reacts with sulfuric acid? Well, if we remember, pure metals always react to lose electrons and form positive ions, so zinc is going to be oxidized because oxidation is loss of electrons. Iron is going to have a less vigorous reaction than magnesium will, because it'll have less bubbles, because think reactivity series. What's higher up? Well, iron is a transition metal, magnesium is group 2, and transition metals generally they're the lower down than group 1 and 2, so magnesium is going to be more reactive, so it's going to have more bubbles of hydrogen gas, and it's going to be more vigorous and faster. And that's very important to remember. So, base is quite a weird word, isn't it? I mean, if you think about it. But a base, by definition, is a substance with a pH greater than 7. You should know the pH scale. I'm sure you know the pH scale by now. You know, 0 to 7 is acidic, 0 to 6 is acidic because 7 is neutral, and then 8 to 14 we call alkalis. But technically, 8 to 14 are bases, because you need to learn the definition of an alkali. Not all bases are alkali, because an alkali is a base that dissolves in water. So if you have an insoluble base, as we'll look at when we're forming our soluble salts a bit later on, that is not an alkali. So an alkali is a base that dissolves in water. So alkalis are things that have a greater pH than 7, but they have to be soluble. They have to dissolve in water. Base is just the overall term for things greater than a pH of 7. So with that out of the way, the word equation for neutralisation reaction. Hopefully you remember this. Acid plus base. You may well remember it as acid plus alkali, but technically we would write it as acid plus base because we can react insoluble bases with acids, so they wouldn't be alkali. So the general word equation is acid plus base and gives you salt plus water. So acids in aqueous solution, they form H plus ions. We say they dissociate or ionize. That's the higher tier topic though. So you just need to remember that they form H plus ions. A H plus ion is just a proton actually, because it has because it's plus, it has no electrons, and if you do your Senecas, you'll know that 99.97 something percent of hydrogen atoms don't have any neutrons either. Alkalis, they form minus OH ions, or probably better to say OH minus ions. That's what they form when they dissolve in solution, because they ionize as well, but that's higher tier term. I just realised I should have put question 13 in bold. It is higher tier only because it's an ionic equation. So here is the ionic equation for a neutralisation reaction. We have H plus ions react with the negative OH ions to produce water. So this is probably the neutralisation reaction you will have looked at. Hydrochloric acid plus sodium hydroxide gives you sodium chloride, our salts plus water. So what essentially happens is we have our H plus ions. They react with our OH minus ions and to form water, while because we have a metal and a non-metal, they come together, react, so they're not really actually spectator ions at all, I was lying, and form our salt sodium chloride. So before we delve into the challenging topic of strong and weak acids, we're going to have a look at what we can use to identify the pH of a solution. Or you should probably have said universal indicator, that's pretty obvious. So pH indicators, they're just essentially dyes that change colour when they're in the presence of the acids or bases. And yeah, they're kind of their universal indicator is probably the one you need to know about. Obviously, when we come down and do titrations, you're going to need to know about other ones that kind of work on a smaller kind of scale. The second one we can use, you probably won't have come across, pH probes. So like electronic devices, we can stick in a solution and it electronically tells us on a screen the exact pH of the solution. Probably more accurate, so if you're being asked about something that's how to make an experiment more accurate about pH probe, unless it's a titration, don't trust titrations. So in this little look at acids, we kind of had a look at what makes an acid, because you may have been wondering, well, we have hydrochloric acid, but obviously, especially in the second video, I talked about like hydrogen chloride. There is actually a difference. They're not the same thing. So what happens between them? So hydrogen chloride, when it's in an aqueous solution, it ionizes. Ionization, it simply just describes the process of an atom turning into an ion. You know, it's like and anything we've looked at, gain and loss of electrons, that's loss of electrons in metals, oxidation of metals, that's ionization, as magnesium atoms losing their outer electrons to becoming ions. Ionization is happening there. So the hydrogen and the chlorine, they both become ionized. So you get these H plus ions and Cl minus ions, chlorine, negative chlorine ions, as the covalent compound has separated, because obviously we look at this as a simple covalent molecule, don't we? We see how hydrogen and chlorine kind of bond together covalently. Well, that separates and they become separate ions in aqueous solution, because hydrogen chloride, that's a gas, but hydrochloric acid you see as a liquid, it's because it's aqueous. We talked about aqueous, what it means, dissolved in water. So acids are formed when some compounds ionize in water. And when they ionize, we say they dissociate to form H plus ions. Now, dissociation is simply the separation of kind of charged particles. So that's kind of where it's ionized and dissociates. It, you know, the charged particles separate. But you need to know that we have strong and weak acids. So strong acids ionize completely in water, which is kind of our aqueous solution in this case. So water, they ionize completely, and this means that all the particles, they all dissociate and they all release H plus ions, whereas weak acids only partially dissociate and only very few of the particles dissociate to release H plus ions. So examples, there's a few examples listed in the specification. Hydrochloric acid and sulfuric acid, we've seen in this video, they're both strong acids, as is nitric acid. Whereas examples of weak acid, citric acid, for example, from lemons, carbonic acids in like rainwater. You may have studied that in geography, I don't know, and ethanoic acid as well. So remember those just in case, you know. So a really interesting thing happens when we have the partial ionization of a weak acid in an aqueous solution. What actually happens is a reversible reaction gets set up, because while some of the acid particles are dissociating to form release those H plus ions, other parts of the acid, they are actually undissociating, coming together with the H plus ions and forming the particle back again. So fill the gaps. For an acid, the higher the concentration of H plus ions, the faster the rate of reaction, because acids react through the H plus ions. The H plus ions are pretty reactive, and that, you know, that's why we see acids in so many reactions, because what happens when acids react with stuff is actually those H plus ions react with it. We saw what happened when acids and bases react back when in neutralisation. The H plus ions react with the OH minus ions, so that's what happens. And I think this is really the challenging bit to get your head around, because strong acids and concentrated acids are not the same thing. Earlier we were talking about the reaction between metal and dilute acid. Dilute acids are not the same thing as strong, weak acids, sorry. The concentration of an acid, that's simply just like, as we talked about the definition of concentration in the last video, it's like the amount of acid that's dissolved in a given volume of water. So it's got nothing to do with the ionization. Whereas strong and weak acids, the strength of an acid just tells you like how much of the acid has dissociated to form the H plus ions, essentially. So we can have dilute hydrochloric acid, that's a dilute strong acid, and you need to be able to identify strong and weak acids. That's why I gave you examples of each. back up here. So the concentration of H plus ions, that's different as well. That's simply talking about like the amount of H plus ions in a given volume of acid, or sorry, I should say solution, the amount of H plus ions in a given volume of solution. So now we kind of learn like a more advanced definition of the pH. So what the pH and the pH scale is actually measuring is the concentration of those H plus ions. So what that depends on is essentially whether it's a strong or a weak acid. So if you have the same volume, the same concentration of an acid, then stronger kind of acids are always going to have a low pH because more H plus ions have dissociated, and it's first of all it's fully ionized, and therefore more H plus ions have dissociated, and therefore it's got a lower pH. But if you have like a really dilute strong acid and a really concentrated weak acid, then you may well get more H plus ions in the concentrated weak acid than the dilute strong acid. So pH kind of takes both into account and just measures the concentration of H plus ions, which ultimately dictates the reactivity of an acid. So a triple science only topic, titrations. This is a required practical coming up. Titrations, I find they can be the bane of a lot of people's lives, but they're actually not that bad at all once you get your head around them. So essentially what we're doing with a titration is we're finding out the volume of an acid needed to neutralize an alkali, or it could be the other way around. We could be finding out the volume of an alkali needed to neutralize an acid. So we obviously need a pH indicator for this. So let's get into the method. So we're going to add a set volume of an acid of known concentration to a conical flask using a pipette. Obviously we use a pipette for this, but then we add in the acid using a burette. So you need to know the difference. It has come up before, asking you for the differences or the advantages between pipettes and burettes. Pipettes are good for measuring, for delivering kind of volumes that you've measured out. So you measure out the volume, you put it in your pipette, you deliver it. Burettes, you can add volumes that you know you need. So you can kind of measure how much is being added as you're adding it, because it has that kind of stopcock at the bottom, which you open and let it out, and drip by drip. However, pipettes are more accurate in measuring smaller volumes. That's quite important. So we have our set amount of alkali in the in our conical flask. We're going to add an indicator. We get on to why we can't use a universal indicator for titrations in question 15. We add methyl orange, I think, is a good indicator to use for titrations because it shows the difference between an acid and an alkali easily. And then we fill our burette to the top. Obviously do it below eye level to be safe. Look for the bottom of the meniscus. That's important. That's one way we can make them more accurate, by looking at the bottom of the meniscus instead of the top bit. The meniscus is obviously the dip in the liquid at the top. That could avoid a parallax error. That's what it's called when we misread a volume due to the meniscus. And then we start to add in our acid. So the first time we do this is kind of an experiment. We need to find like the rough area where the acid gets neutralized. So we're adding it it's quite slowly, but not too slowly. But as soon as the alkali in the indicator changes color, we can tell that neutralization has occurred, and therefore we've gone past our known volume of acid. Stop it immediately, and we look at how much acid has been used up. Note that volume down, and then repeat it. And on our second one, we're going to go down, and as we approach that volume of acid needed, we're going to slow down until we're doing it drip by drip by drip and swirling it around to make sure it's all reacting. And when that color change happens, then we stop it, and if we repeat this a couple more times, we should get an exact volume where every time we do it, you know, to 1 decimal place, centimetre squared perhaps, we get that exact volume every time it happens, that exact volume, because obviously these concentrations, if you looked through concentration in the last video, you know they're exact. So we need an exact volume of an acid of that concentration to neutralize the alkali. And that's what we do titrations to find out. We find out that volume, and therefore, with that volume, we can find out the concentration of the unknown acid as well. That's the second thing we can use titrations for, finding the volume of either an acid or an alkali to neutralize an acid or an alkali. And we should know the volume of the acid or alkali we're putting in the conical flask, but likelihood is we don't know the volume of the acid or alkali we're putting in the burette, because if we did know, we could do a quantitative chemistry calculation and figure out the volume we needed without having to do a practical. But if we don't know the concentration, we do the practical to get the volume, and then we go and we what else can we find out from concentration? This is higher tier as well, because it involves complicated calculations. We can go and calculate the concentration by, you know, we can use concentration equals moles divided by volume, because we can work out the moles from the chemical equation. We can use our mole ratios and then figure out the, you know, the moles of the unknown solution, and we got the volume of the unknown solution, so that we can divide one by the other to get the concentration. Again, that's a very rudimentary explanation. You really want to go and check the last video on quantitative chemistry, the concentration section. We cover a calculation that you might see from a titration, and converting from moles to decimeter cubed to grams per decimeter cubed, because that's important. That's in the specification as well. You will need to do that. So that might all come up under titrations. So if you're not sure about how to do that, go and check the previous video. So 3 things we can do to make a titration more accurate. Again, repeating it a few times, getting the same value over and over and over again, and then calculating a mean, ignoring values that are far out, such as our first value when we've only found a rough estimate. Also reading from the bottom of the meniscus, as I talked about, avoiding those parallax errors. To keep it safe, obviously, we want to wear goggles because we're dealing with acids and alkalis, you know, going to corrosive damage our eyes, and you know, we make sure our eyes and our head is above the burette, because so that we don't spill any acid into our eyes. That's a safety point as well there. So we can't use universal indicator for titrations. I briefly touched on this back up here. Universal indicator gradually changes colour because it's made up of lots of different dyes that gradually change colour. Methyl orange, the one we use for titrations, that captures the sudden colour change as soon as the neutralisation has happened. It changes colour, and you should know that methyl orange, it's red in acids and yellow in alkali. And if you might not have fully got that, to be fair. I was only talking through it. So go and look up a picture of a pipette and a burette and how the experiment is set up, because it might make it a bit more clear. And obviously, if you haven't done it in class, you might not have understood anything at all. But I would hope that you'd have done this in class. So if you haven't, maybe go and look up a video of it being done, because there are videos out there. So now we're going to get onto the soluble salts practically. And you need to know that we react an acid and an insoluble base together to form a soluble salt. So an insoluble base is one that's not going to be an alkali. That's very important. So we have some examples of insoluble bases here. Metal oxides, metal hydroxides, metal carbonates. You need to know what they all form. So acids and metal oxides are going to form salt and then water, because obviously you have the leftover hydrogen and oxygen are going to form water. Acid plus metal hydroxide, also salt plus water, but obviously the equation is probably going to be slightly differently balanced. And acid plus metal carbonate, we have a carbonate in there, so we're going to get salt plus water because the 8 means we have oxygen in it, and then the carbon is going to form carbon dioxide. So acid plus metal carbonate gives you salt plus water plus carbon dioxide. That's very important to know. Have a practice with these 4. So here we have our first one, acid plus metal is salt plus hydrogen, because it's just metal, so we're not going to get any extra oxygens or carbons or anything, so it's just going to be hydrogen. I don't think you'll need to know the symbol. Actually, it's probably worth knowing the symbol equations for the acids. This is sulfuric acid, H2SO4. SO4 is a sulfate, essentially. That's probably worth knowing. It'll at least make understanding things a bit clearer. But what you should very much be able to do is name the salt formed in the word equation. So what would we call FeSO4? Iron sulfate. So this is a sulfate, this is iron, this is hydrogen sulfate, but because it's an acid, it's gone into the aqueous solution, fully ionized and dissociated, and we call it sulfuric acid. So again, name the salt. Copper chloride here we have, and we need to balance it, adding a 2 here because we have 2 hydrogens and 2 chlorines on this side. So here we have potassium hydroxide plus nitric acid. This is nitric acid here, HNO3. These are the 3 strong acids that you need to know about. Reactions with weak acids I don't know too much about, but you need to know more about the reactions of strong acids. So if you're struggling to form the salt, here's a tip. We kind of what we're doing is we're essentially removing the hydrogen, removing the H plus ions, and replacing them with the metal to form that metal-non-metal ionic compound, which is a salt. So we're removing the hydrogen, getting our non-hydrogen acid bit, and taking the metal, putting it with that, and forming our ionic compound, salt. That's a good way to remember. And then our leftover ions come together and form usually water, but sometimes hydrogen if we don't have an extra oxygen here, or carbon dioxide if it's a carbonate, which is exactly what we've got happening here with calcium carbonate here and hydrochloric acid. You should be able to work out the chemical formula for this salt because it's simple. A simple ionic bonding thingy, the empirical formula. Obviously we have calcium and chlorine here, but we need 2 chlorines for the 2 electrons of calcium because this only has 1 gap on its own. Again, check the second video. But if you're confused, it's likely because you don't understand the concepts of video 2 and bonding. And then again, the concept, chemistry, we're constantly building on concepts of the previous video. So this is kind of bringing all of our concepts together here. And as I keep talking about understanding how to face the unknown compounds they're going to throw at you and being able to identify, okay, this bit's a metal, this bit's an acid, so they're going to react to form a salt and a hydrogen, and I know that to form my salt I'm going to take away the hydrogen and replace it with a metal, and that's how I form my salt. It's kind of that ionic compound, and then I can figure out its name from the metal bit plus the name of the non-metal bit. So with metal carbonates, we get our salt plus water plus CO2. That's important. So this is the soluble salts required practical now. And it very much also draws on the separation techniques, filtration and crystallization, that we looked at right way back at the beginning of the first video. So you might need a refresh on them, but I'll give you a brief explanation here. So obviously we're reacting our acid with the insoluble base, our insoluble base being metal, metal oxide, metal hydroxide, metal carbonate, those kinds of things. So what we're going to do is we're going to warm up our acid because, we need to make it a bit more reactive, so we're going to warm it up. And then we're going to add our insoluble base a bit at a time, and we're going to keep adding it until no more reacts. So when no more reacts, we're obviously going to see that insoluble base left over at the bottom because it's not going to dissolve because it's insoluble, so it's going to be left over at the bottom. If you want to talk about it in terms of limiting reactants, we react until the acid becomes the limiting reactant, so we use up all of the acid in the reaction. Go back to video 3 if you're not sure about limiting reactants. So once we've got our solution, our salt, which is dissolved in our solution because it's just reacted, it's dissolved in the solution, and also a bit of the insoluble base left. First of all, because we want pure dry salt crystals, we need them to be pure, so we've got to remove all traces of the insoluble base. How are we going to do that? Separation technique time. Filtration. We're going to get our filter funnel, put some filter paper in it, pour our mixture through. The insoluble solid is going to be separated from the solution, so we have that insoluble base. It's going to be stuck in the filter paper, whereas the soluble salt is going to go through the filter paper and into the conical flask below. And when we've done filtration, we've got a pure sample of that salt in our well, not actually, no, sorry, I say pure, it's not pure, is it? Because we have both water, which is our aqueous solution, and the salt dissolved in the water. So what we're going to do So we've looked through reactions of metals and acids and metal carbonates and hydroxides. We should be experts in chemistry by now. But there is one more thing we need to look at in this topic, and that is electrolysis, because it's what we use to, separate those metal compounds with metals that are higher up on the reactivity series than carbon. So if you want to pause the video and have a go at these 17, remember the ones in bold about half equations, reduction in terms of electrons, and half equations. That's higher only, so if you're foundation, don't do the ones in bold. So here is the diagram for, this is basically what electrolysis looks like. We have the power supply here. This is the symbol for a cell or a battery. That's obviously because it's electrolysis, it's going to use electricity. That's how we break down the ionic compound. So what is an electrolyte? Well, an electrolyte is simply a solution that can conduct electricity. It can conduct electricity because it's an ionic compound, and therefore when it's either dissolved in water or molten, the ions are free to move about and carry charge. Obviously solid ionic compounds can't be used because their ions are in fixed positions, so they can't move. So the electrode is like the solid that conducts electricity, and it's basically what we use to transfer electricity into the electrolyte essentially from our power pack and get a full circuit, because obviously if this is all charged, then charge can flow all through and we can form a complete circuit. So because we're dealing with the flow of electricity, we're going to have a positive and negative electrode, and they have special names. The positive electrode is called the anode, and the negative electrode is called the cathode. You can use the acronym PANIC to remember it. If you're panicking in the exam, just remember PANIC. Positive is anode, negative is cathode. So, you know, you have a way of remembering it there. So, especially if you're in higher tier, you need to know what happens at each electrode as well. So obviously we're going to have positive and negative ions. So the positive ions are going to be metal ions, because that's what metals are. They always form positive ions. Positive gets attracted to negative, so they will come over, be attracted to the cathode, the negative electrode, and they will gain electrons to form atoms. Obviously if it's negative, it's going to have more electrons, so this has spare electrons, and that's because the flow of charge goes from positive to negative, because we have our negative non-metal ions in the electrolyte get attracted to the positive electrode, the anode, and they lose their extra electrons to form atoms, and those extra electrons, they get taken around, as this is the flow of charge, isn't it? And they get taken to the negative electrode. So if I asked where oxidation and reduction happen, where does the gain and loss of electrons happen? Well, the loss of electrons happens at the positive anode, because we have these negatively charged particles giving up their electrons. Reduction happens over here at the cathode, where we have our positively charged metal ions gaining electrons and therefore being reduced. Again, there's lots of kind of flips, because you have positive going towards negative and then gaining electrons. So you really, when you're talking about electrolysis, you've really got to think through each step logically, because if you said the positive ions and you think, oh, positive ions, positive electrode, anode, then that wouldn't be correct, because the positive ions go to the negative electrode, the cathode, the negative ions go to the positive anode, the positive electrode, the anode, because opposites attract, and that it can get pretty confusing, so you have to really think through every step. I should also mention that we use a DC power supply, so if you're asked to draw a diagram, make sure you label it on as DC. So, the electrolysis of aluminium oxide, I think question 5 was, how does that work? What happens? Which ions go where? Well, our positive metal ions, remember, which will be our aluminium, they will go to the negative electrode, so we have our Al3+ ions come this way. And what happens is they gain, obviously, electrons at the cathode, the negative electrode, and then they sink to the bottom as the molten aluminium metal. So here we're talking about the electrolysis of molten kind of ionic compounds. So we've melted it at incredibly high temperatures into molten aluminium oxide. The aluminium has come over here, gains electrons, formed pure aluminium metal, and it has gone down to form a layer of aluminium, pure aluminium at the bottom of the tank. At the anode, the positive electrode, it's going to attract the negative ions, and in aluminium oxide, those are going to be the oxygen ions, the O2-. You need to know that they're 2- because they're group 6. Aluminium you don't need to worry about so much because it's a transition metal, but oxygen's going to form 2- ions. It's going to come over, it's going to give those extra electrons up and form oxygen, just an oxygen atoms that float off freely as oxygen gas, because, you know, they've stopped being ions. Now, in the electrolysis of molten compounds, it's very interesting. We often add other types of compounds because most metals, especially transition metals, have an incredibly high melting point. So in the case of aluminium oxide, we add cryolite, so like an aluminium compound, but cryolite has a lower melting point than aluminium oxide, and this lowers the melting point, which means we need to put less energy in to get our products. Okay, so can you finish the chemical equation for the electrolysis of aluminium oxide if I told you this was aluminium oxide? Well, these are the products we get, aren't they? We have aluminium atoms and O2 atoms because they're diatomic. So then balancing it, this is what it comes out to be. Now, if you're higher tier, I'd like you to have a go at writing the half equations for what happens at each electrode, or oxidation or reduction. So oxygen at the anode is oxidized. Oxygen is oxidized. That's quite weird to get your head around, but obviously at a higher tier we need to know that oxidation is about electrons, not oxygen in reality. And then the tricky part might have been balancing this, because oxygen is diatomic, so we need to put two oxygens in to get each oxygen pair out. So therefore, because each oxygen is 2 minus, and we have two of them, 2 times 2 is 4, so we need 4 electrons coming out. And then here we have the reduction of aluminium ions, they're 3+. We got told that here, so you should have been able to work out that we need to add 3 electrons to form aluminium atoms, which then, in the case of electrolysis with molten ionic compounds, they sink to the bottom. So, as I mentioned, electrolysis is where we decompose ionic compounds, which essentially just means we're breaking them up into smaller parts, therefore they're individual parts. And we, as I also mentioned, we use electrolysis to separate kind of metal oxides, and because we find them naturally, but metals that are higher reactivity than carbon, so we can't use reduction, which we talked about earlier. The disadvantage of using electrolysis is that we have to heat it up really high for the molten compounds to melt, so that we can get the molten compounds, so that we can melt the ionic compound. And that costs a lot of money to get that energy, so whether it's cost effective is difficult to say. I think we talked about which electrode reduction happens at. Reduction, the gain of electrons happens at the cathode, because the positive metal ions come in and gain electrons to form metal atoms, pure metal. And finally, the anode, the positive electrode, that is made of carbon, or a carbon compound. It's made of a form of carbon, and it needs to be replaced regularly because it reacts with oxygen while it's there to produce carbon dioxide, especially because when you get the, for example, in aluminium oxide, if the oxygen's going over there, it's actually can react with the carbon anode, and that's why it needs replacing, because obviously it's being slowly turned into carbon dioxide. So instead of spending loads and loads of money on heating ionic compounds to 2000 degrees so that they melt into molten compounds, we can do electrolysis in aqueous solutions, where we dissolve ionic compounds in water in that aqueous solution, and therefore their ions are free to move about, and therefore they can conduct electricity. However, it is different, and there's a key difference, because the water that we dissolve the ionic compound in, that water can also partially ionize and dissociate. So as well as the positive and negative ions from the ionic compound, we have a few H+ ions and OH- ions knocking about as well. So for the electrolysis of sodium chloride in an aqueous solution, we would have the positive sodium ions, the negative chlorine ions, but we would also have H+ ions and OH- ions, which will have partially dissociated, partially ionized and dissociated in the solution. And because we have 4 different ions floating about, any one of them could be drawn to the positive and negative electrodes. So as well as the negatively charged chlorine, the OH- could also be drawn to the electrode, the positive electrode. But we only get one, and there's rules to remember why. So at the anode, the positively charged electrode, as I talked about, we get the negatively charged ions. So we could have chlorine, or we could have our OH minus ions from the water. How do we know which one? Well, if a halide is present, so a halide, I mean a halogen ion, that's what we call halogen ions, halides. If you remember back from video 1, we went through group 7, the halogens, so that's like fluorine, chlorine, bromine, iodine, astatine, I think is the next one as well, but that's radioactive and we don't really talk about that. So if a halide ion is present, then that will be what is drawn to the anode. However, if no halide ions are present, so for example aluminium oxide, the negative ion is oxygen ions, sorry, then the OH minus ions will go to the anode instead of the oxygens. So if we take our example of sodium chloride, we have to think we have our chlorine ions, our OH minus ions. We check, is chlorine a halide? Yes, it is. So therefore, at the anode, in the electrolysis of sodium chloride in an aqueous solution, chlorine will form. So the cathode, the negative electrode, it's where the positive ions go to gain electrons, because that negative electrode is going to have more electrons, so they go to gain electrons. And how we will have the positive metal ion and the H plus ions, and if the metal ion that we have is less reactive than hydrogen, then that metal will form at the cathode, but if that metal is more reactive than hydrogen, then the H plus ions will go to the cathode and form hydrogen. So you can probably see now why we include hydrogen and carbon on the reactivity series, even though they're not metals. It's because hydrogen we use for electrolysis, and carbon we need to know reactivities for reduction. So let's take our example of sodium chloride. We have our positive sodium ions and our H plus ions, and we have to consider, well, which one is sodium more or less reactive than hydrogen? Well, sodium is more reactive than hydrogen because it's a group 1 metal. Hydrogen is pretty low down on the reactivity series. Sodium is pretty high up because it only has 1 electron on its outer shell to lose. Even some transition metals like iron and zinc we learn are higher up than hydrogen on the reactivity series. So in the H plus ions will go to the cathode, and hydrogen is formed at the cathode in the electrolysis of sodium chloride in an aqueous solution. So here's what would happen at the anode, our half equation for the anode. We would have chlorine as a negative ion. Obviously it would lose electrons in oxidation as it's a negative ion, so it's going to have more than enough, too many electrons to be an atom, so it needs to lose them. And because chlorine is diatomic, because it's in group 7, we have to balance it appropriately. So here's the half equation for the reduction of hydrogen. Obviously, again, hydrogen's diatomic, so we have to balance it. But yeah, we can see here H plus and negative electrons going in to make hydrogen atoms. So what if the metal formed at the cathode instead? Let's take copper because it's less reactive than hydrogen. Well, this is what it would look like. We would have Cu 2 plus, so we would need 2 electrons because it's 2 plus, so it has 2 less electrons than protons, so it needs 2 more to be a neutral atom. And then at the anode we would have the oxidation of negative hydroxide ions, OH minus ions. See if you can figure out the half equation for this. It's kind of tricky. So this is what OH minus ions form when they're oxidized and lose electrons. So they form oxygen and water. This is something you just have to learn. There's no easy way to remember it. You just have to learn that the oxygen and hydrogen are going to form water, and then you obviously also get this electron. However, you may have noticed we need to balance half equations. That's very important. So have a go at balancing this. Well, that's quite a tricky one to balance, but that's how you do it. We have 4 OH minus ions and therefore 4 electrons get lost from each, and then we have 2 water molecules for every 1 oxygen molecule. So the diagram for the electrolysis of sodium chloride in an aqueous solution would look pretty much identical to aluminium oxide, apart from there would be no metal layer forming at the bottom. It's worth noting that if the metal does form at the cathode in electrolysis of an aqueous solution, so for example if we get copper at the cathode, then that copper is just going to form a layer over the cathode. It's not going to sink to the bottom like aluminium does in molten electrolysis. So there's final challenge question for anyone that's doing higher. Have a go at figuring out what's going to form at each electrode. So do it for the anode and cathode. Figure out what's going to form and then write the half equation for it. So at the cathode we get our metal is zinc more or less reactive than hydrogen. It's more reactive, so we're going to have this half equation because hydrogen's going to form. And at the anode, do we have a halide ion? No, we don't. We have a sulfate ion. So we're going to have negative OH ions forming, and this thing to write out, you may need to write out any one of these, so make sure you're happy with crafting up half equations if you're higher tier. Finally, it's worth noting that for some of you the electrolysis of an aqueous solution is a required practical, so you may need to write a method for it, but that's simply just writing about how you'd set it up with your DC power supply, your electrodes, and being able to figure out what forms at the anode and cathode. You may be asked how you can test for the gases that form. So hydrogen, if you put a lighted splint into a test tube of hydrogen, there'll be a squeaky pop sound. Oxygen will relight a glowing splint that you've just put out, and chlorine bleaches damp litmus paper white. So those are the three gas tests for oxygen, hydrogen, and chlorine. You need to know those for paper 2, but obviously for paper 1 they may well come up as well, because a lot of the chemistry content is linked between papers. So I know this was a long video, but we've made it to the end. If you've watched all the way through, we've kind of been putting together everything we've learned in chemistry so far to work out how our random compounds react with each other, with acids, with water, with metal hydroxides. It's been quite a complicated journey, but I hope you've been with me and you've understood how redox reactions, half equations work. And obviously, if you're higher tier as well, how strong and weak acids work, what ionization and dissociation are, as well as what alkalis actually are, writing word equations, balancing symbol equations, ionic equations, titrations, very important if you're doing triple science, they're coming up, and forming salts. I hope you're able to figure out the names of the salts now, that's very important, and obviously the soluble salts practical is coming up for everyone, and finally electrolysis. So we have all of the questions there. Before the exam, make sure you go through them all, make sure you can answer them all, and then obviously come back to the questions you got wrong the next day. Practice some exam questions maybe, just to get prepared for what you might see next Friday. And yeah, I hope this was helpful, and please subscribe if it was. And I hope you kind of understand chemistry a bit better now.